Thank you. Hello, everybody. So my name is Pavel Jachym, as you will see in the beginning of the presentation. I'm from, as Teresa said, from the Astronomical Institute of the Czech Academy of Sciences, which is located near Prague, but one department is directly in Prague, so I'm from Prague. And I'm also part of the Czech ALMA node, so the Czech node of the European ALMA Regional Center, which I did not specifically written here, but you can see the logo here. And I will give you more details about the EU ARC later in the presentation. So very brief outline of my talk. I want to first give you some more general information about the ALMA observatory. I'm not sure how many of you are familiar or using ALMA. Then the substantial part of my talk should be about the wideband sensitivity upgrade of ALMA, which is ongoing, and it will be a very important step in the ALMA lifetime. Then brief information about the Czech ALMA node, as I already noted. And in the second part of my talk, or by the end of my talk, I want to talk more about what I'm doing and about gas stripping from galaxies and also ALMA observations. So some general information about ALMA, Atacama Large Millimeter Submillimeter Array, and I will try to quickly touch the four questions. Who is responsible, or who is running ALMA, who built it, where it is, how does it work, and why we need ALMA. So this is really quite general information, but maybe you can quickly look at this plot. This is comparison of how ALMA, where ALMA stands compared to the wavelengths or frequency and the angular resolution to other observatories, major observatories. This is probably a little bit outdated, but I think most important observatories are included in the plot. So obviously ALMA is operating at the millimeter or sub-millimeter wavelength range, and the angular resolution is unprecedented in that frequency range. For comparison, you can see, for example, the IRAM NOIMA interferometer, which is located in France, in the northern hemisphere. ALMA can do both imaging and spectroscopy in the millimeter and sub-millimeter wavelengths, and it is needed to to combine with the observation from the other observatories in other wavelengths to get the full image of the physical processes in various environments. Obviously, it has shown that it can bring transformational research in the physics of cold universe, so optically dark universe, molecular clouds, first galaxies, first stars, etc. And so this is really the basic parameters about ALMA. So ALMA has 66 antennas. 50 are 12-meter antennas, which form the main array of the telescope. Then there is so-called ACA, Atacama Compact Array, which has 12 smaller antennas, 7-meter diameter. And then the third part is Total Power Array, which has 4 12-meter antennas for single dish observations, also called total power observations. And this is very unique combination because it using all three arrays allows you to basically cover the range, the full range of spatial scales in the observation. So you need the ACA or the total power to see not only the most compact features in your targets, but more extended features. So if you are observing a complex target which has compact features as well as extended features, you basically need to combine the observations from all three parts of the observatory. Then there is 192 so-called pads, and the antennas can be moved into different configurations from a baseline from 15 meters to 16 kilometers. And as I said, the more extended arrays, well, I didn't say that, but more extended arrays, the configurations of antenna where the baselines are larger will give you obviously the higher spatial resolution, and more compact arrays then give you a better sensitivity for extended sources. The range of frequencies and wavelengths you can see from roughly 10 millimeter to 0.3 millimeters, and there are 10 bands covering that range. You can do polarization observations and many other types of observations, so this is just an example. Okay, who is responsible for ALMA, or who is running it? So it's really a global collaboration, and we as Europe, we have 37.5% share in ALMA, and it is ESO for Europe who is involved in the operations of the observatory. And as I mentioned in the very beginning, there are regional centers. So I mentioned the European regional center, but there are 3 to help users of ALMA and to help or to assist the community of ALMA users worldwide. There are 3 regional centers, one in Europe, one in North America, one in East Asia. And these centers are supposed to provide support to people who need help with observing, with data, basically anything related to ALMA. So quickly about the site. There are 2 sites. One is a so-called array operation site, which is at 5,000 meters in the northern Chilean Andes, at 5,000 meters, and this is where the antennas and currently where the correlator is. And then at 3,000 meters, roughly 3,000 meters, there is OSF, ALMA Operation Support Facility, which is a base camp for everyday operations of the observatory, and when some maintenance of the antennas, some more substantial works are needed to be done, then this is the place. You can see the location of ALMA, minus 23 degrees, and correspondingly you can observe targets up to 47 degrees in declination. So it's a southern hemisphere, but there is still some part of the northern sky which can be observed. It's always quite fun to look at the place, at the location. So this is this is below the mountains. So this is the Atacama Desert. You can see the nearby town or city of San Pedro de Atacama, and then this is the lower, this 2,900 meters OSF, ALMA Operation Support Facility. I don't think this is a very current view of that, but now it's more. I think there are more things nowadays. And then this is the high site at 5,000 meters, so you can see the ALMA antennas. This is the building where the correlator is located, so where all the signals from all the antennas meet and are correlated. You can also, at the same image, you can see here, this is Apex telescope. It's a single dish telescope which is currently run by the Max Planck Institute in Bonn. And the last view, so as I mentioned, you can change the configurations of the antennas, and they have very cool transporters for that, which are able to grab the antenna and move it to the new location. Right, so why ALMA is in Chile and in such extraordinary conditions or locations? This is because at the wavelengths of millimeters or some millimeter, the atmosphere is not quite transparent. So you can see for the range covered by ALMA, what is the transmission of the atmosphere. You can see here from B1 to B10, this is the 10 bands with which ALMA is equipped and does the observation in. And I think it says 50 times the conditions are better than the blue line, and some 12-13% even than the black line. And you need for the lower frequency observations, you need good conditions. So this is measured in this PWV, so 1 millimeter, which is easily achievable there. You can easily observe low frequency in lower bands, but you need below, let's say, 0.5 millimeter for higher frequency observations. And this is how the conditions look like over the year. So the best conditions are roughly from April to December, and the green, I think, is the or you can see that 50% of time roughly in this region or in this period of year, the conditions are better than 1 millimeter of water vapor. So this is what I already mentioned, 192 pads or locations for the antennas, and you can have 10 configurations ALMA, from the most compact, which looks like that, or to the most extended, up to 16, roughly 16 kilometers. So this is one of the most extended configurations, and there is a schedule over the year when the antennas are moved to different configurations, and then not every year the highest or the most extended configurations are reached. So it's every 2 years. Okay, I think I'm not very fast. So what millimeter astronomy or observations can do, I think I already mentioned that, and you probably know all this. But the main aim of building ALMA, or there were these 3 level 1 science aims. You can read it, but it was basically quick observations or detections and mapping of the most important molecular lines in the Milky Way galaxy at redshift 3, then map dust emission and kinematics in protoplanetary disks in young stars, and be able to provide high fidelity imaging at high resolution. And basically all these goals were achieved already. And so now I'm going to the second part of my talk. So we need, better observatory. So we need an upgrade. So this is why I think in 2018, ALMA published this so-called 2030 development roadmap, and new goals were defined for the years, for the decade 2030. You can read it by yourself, but they are quite ambitious, and the main regions or areas are origin of galaxies and detecting the at this rate, at the high rate, key elements in first galaxies at high redshift through redshift of picostar formation, detecting CO and atomic lines at this rate. Then the second goal is the origin of chemical complexity. So again, at some rate, you want to be able to observe 2 to 4 protostars per day and trace the complex or the evolution of complex molecules in star formation and planet formation down to solar angular scales, and the last goal is origins is in the origins of planets, and the goal is to be able to image protoplanetary disk in nearby star forming regions, and to resolve down to one astronomical unit, and to see in the dust continuum the tidal gaps and holes created by planets which are under formation. So these were the new goals, and basically for all of them increased bandwidth and increased sensitivity of the observatory are necessary. So this is the big project which is now ongoing and which I mentioned. So this is the wideband sensitivity upgrade, and maybe I will move here. So you know that. So ALMA is becoming a little bit old, and to keep it modern, we want to do an upgrade. And the main goals, as I mentioned, is to increase the bandwidth, the instantaneous bandwidth which is available, and the goal, or at least the increase should be by a factor of 2, and the goal is by a factor of 4. And to do this at the same time have a lower noise in the observations. And another goal is to improve the sensitivity of the receivers and of the whole digital signal processing of the telescope. And so it will help to increase the observational capabilities of ALMA. And basically it means ALMA will become a totally new telescope in roughly, or by the end of let's say by the end of in year 2030 or something like that. So this is a scheme what needs to be upgraded. So basically, well, we will not change the antennas themselves, but basically everything else will be changed. So going from the receivers, so you can see this is a view on the front end cabin, the 10 receivers, or I think they are probably not all 10, I'm not sure, because band 2 is still in development, but the receivers, then the digital signal path, including the IF processor, digitizers, and data transmission system. Then there will be new connection, new optical fiber connection from the high side to the OSF, because the new correlator, which is a huge part of the upgrade, will not be located anymore in the high side, but will be in the OSF in the 2900 meter. So new correlator, and connected to that is also an upgrade of the basic or the major software tools and control and telcal and pipeline and observing tool, etc. So this is a big thing, and I will not read all this, but many things are already happening. So there in development there are first wideband receivers, band 2, which were missing. This is the last band which is not at the telescope, and second version of band 6, band 8. And the North American are responsible for the new correlator attack. You can read the basic properties, and for example the Europe is responsible for the new fiber connection from the high side to the low side. So as I mentioned, in development is band 2 and second version of band 6. So quickly, so for band 2, it basically combines the frequency range of the originally planned band 2 and band 3, so it will be much wider, and with the upgrade you will be able to cover a huge range of frequencies and lines at the same time. Similarly for band 6, it will be a little bit wider than the current one. I think band 6 is one of the most used bands at ALMA, and the increased bandwidth of band 6 will allow you, so this is how it looks currently. You have these two parts which you can observe, and this is with the new receiver in development. It will be much wider, and it will, for example, allow you to cover at one the full suite of CO2 to 1 lines, etc. So how this will proceed? So good news is that there will be a parallel deployment, so it will be possible to use the old ALMA at the same time as doing the upgrade. Obviously this is a huge thing, so it will need a lot of effort, and it will take for some time away some of the observing time which is available for the community, but it will be possible to run it parallelly. So it will be possible to run the old way and the new way at the same time, and you should expect as the community that especially between cycles 2 and cycle 15 there might be some reduced observing time which is available to the community, and also reduced number of antennas, etc. But then by cycle 15 or so the new ALMA should be ready. So this is the overview of how much better ALMA will be. So basically I think these words like faster, more flexible, more sensitive, and allowing ultra high spectral resolution observations, this is what characterizes the new ALMA. And so the first thing is the instantaneous bandwidth. So it will increase, as I said, by a factor of 2 and ideally by a factor of 4. The correlated bandwidth, so this is the part or the frequency range which you can really observe and do the correlations at some frequency resolution. So there is a huge increase. It will increase by a factor of 4 up to almost 70, and it is important to mention this huge increase is thanks to that you will be able to maintain high spectral resolution. Currently you can reach quite high spectral resolution, but the bandwidth, usable bandwidth, is very limited. Then the spectral scan speeds, spectral scan is when you want to observe a part of spectrum and be able to detect as many lines as there are. So there you can expect a factor of 2 or factor of 4 increase in that. Also for spectral line imaging, this is quite, well, this is a little bit surprising, but even if you are interested in one line and you don't basically need this higher bandwidth observations, but thanks to the new way of the signal, there will be an increase in speed. So basically ALMA will be more sensitive, and you will be able to do your line observation 2 to 3 times faster than now. Obviously continuum will be much better because the bandwidth will be hugely, or 2 times or 4 times more extended, and there will be also a possibility of these ultra high spectral resolution observations, and there will be a zoom mode which will allow very high spectral resolution. I have a little bit more information about these upgrades, so I will probably go quickly through that. So the figure on top, or plot on top, this is an overview of basically just simply showing the bandwidth increase. So these are the current bands there are. Most of them are 8 gigahertz. Band 9, 10 are 16 gigahertz. Here you can see the bands which are under development, 2 and 6. Already they are wider than what is available in the current bands, and this is the 2030 minimum goal, and this is the 4 times goal. So hopefully this will be done. Then for the spectral resolution, well, you can read it here. What are the channel widths and the bandwidth? But again, you can see here in this plot, the blue is the best case you can have with ALMA now in different bands. So it means in each band, if you want to observe with the best spectral resolution, the highest velocity resolution, then the bandwidth, the frequency range which you can cover is quite limited. And with orange again, this is the WSU goal. So you can see huge factors in the band 1, 2. It's almost 70, but in all the bands. For the spectral surveys, as I mentioned, you will have higher bandwidth, so you can again gain huge factors in these spectral scan speeds in the efficiency of the observations. This is not very well visible, but this is an example for the band 2, which is under development. So you can see if you required the best resolution possible now, you would need to so many setups with the current ALMA, and with the goal of, or with the new band, or with the WSU goal, you would only need, let's say, 2 and 2 tunings. So again, much faster, much more efficient. A little bit information about the ultra high spectral resolution. So currently, if we take 100 gigahertz, you can have 92 meters per second is the best frequency resolution. But you have, as I mentioned, very limited bandwidth. So this is only 0.2 gigahertz where you can observe with this resolution, while with WSU you will have better 40 meters per second, but for the full bandwidth of 8 gigahertz. So you can see this is a huge difference. And there will be also this zoom mode, which I very briefly mentioned, and it will allow even much better spectral resolutions. Okay, maybe just mention that. So because you know, we will have more frequency range covered and wider bandwidth, so also the quality of the observations will be better. The coverage of the UV plane will be better. You will have more measurements in the UV plane. So this is for the 2 times bandwidth or 4 times bandwidth, and this will allow to you know, extend the range of possible calibration options, or even use some new calibration strategies, because the sensitivity of the calibrated observations will be better, and you will be able, for example, to do faster calibration cycles, etc. So really the impact of the upgrade will be very, very wide. Okay, this is everything, all the areas, scientific areas, will be impacted by the WSU. I prepared a couple of slides for selected topics, so I will go through them. So for example, for star formation, there are obviously plenty of open questions, and the trouble or the challenge with observations of star formation is that there is a huge range of scales going from molecular clouds and filaments. Clouds are filamentary, which are on scales of 100 parsec, down to the dense prestellar cores and the circumstellar disks. So you see the range of spatial scales is huge, and at the same time there is a huge range in densities and variations in temperature which are involved in the star forming processes. So it drives a complex chemistry. So there is an image of protostellar environment, and you can see in this schematic view different molecular species which trace different parts of the environment, and with the WSU, so with the new ALMA, you will be able to observe almost all of these species which are in this image at once with one single tuning of the telescope. And this is an example. So this is a comparison for there is a PILS, so-called PILS survey of this protostellar binary, and with so this is what they did. So this is the range of frequencies that they covered, and with the extended bandwidth of ALMA, you will be able to do well much more in a single tuning. For origins of galaxies, well, this is you can see the relation between the frequency, basically between the frequency bands of ALMA from 1 to band 10, and redshift. For on the left panel, this is CO lines, and on the right hand panel, this is some atomic lines, important atomic lines going from C2 through O3. And I think I'm writing it here, but well, it's giving you giving an overview of the important atomic and molecular lines to observe high redshift galaxies, and obviously it will be much easier to do these observations and do these detections with the upgraded ALMA. Then spectroscopic redshift surveys. If you want to confirm spectroscopically the redshift of galaxies, it will be much easier because you will be able again to, with sufficient spectral resolution, observe at the same time large bandwidth. So we will be able to detect the lines which will confirm the redshift of the galaxies, which were known previously photometrically with a big error, for example. So this is again illustration. You can read it, but this is again illustration. What was done you need 5 tunings to cover basically band 3 to do this follow-up confirmation of redshift for a sample of galaxies detected or discovered with the South Pole telescope. And this is again the 2 versions of ALMA 2030. You will need only basically 2 tunings. And I will not go into the details, but well, for outflows it will be also quite important, because for outflows which have very wide line width, very big line width, over 2,000 kilometers per second, with the current setup or with current ALMA, you can get into troubles because you are not able to cover basically the whole width of the line. So you may get a non-detection, but it's not clear why it is, whether it is because there is no signal or you're just missing the line. So with the new upgraded ALMA and with the big bandwidth, you will be able to safely cover those wide lines and see the continuum around and do the subtraction of continuum. So you can see here again for different frequency bands, this is the 2 times or 4 times upgrade, and this gives you the velocity with which will be available. So in the ideal case, in the highest frequencies, you will still be able to cover more than 5,000 kilometers per second width. Okay, so there obviously will be more related upgrades. One which is not, I think, part of the WSU ESO is the development of the new generation observing tool. So those of you who use ALMA, you know that you need to use the observing tool to prepare the proposals. So currently there is under development a new generation of that, and I think in cycle 12, so quite soon we should expect this to be ready, and then the new generation observing tool then will later incorporate the changes which will be part of the WSU, and just for fun and for more distant future, I think these are four options which are mentioned for even more distant development of ALMA. So obviously want ideally even higher resolution, so you can increase the distance by which the telescopes, the antennas, can be set apart, so by a factor of 3 maybe. There was an idea that antennas could be part or connected to the array being at the low site, which is I think about 30 kilometers away. There are studies for placing or installing to the focus the plane arrays, or obviously you can increase the number of antennas. This is probably a quite expensive plan. There are also plans for large single dish submillimeter observations, which would be very useful for parallel observations with ALMA, but this is really for a more distant future. So how is it with the WSU and the community? Does community know about that? There is most of the information I was showing is part or taken from this ALMA memo, so you can find it online, and this is a great document with a lot of details. You can find and read it, and there are more examples of how the WSU ALMA will be better for science observations. There was in June actually this year there was a workshop organized by ESO to inform the community. So community I think is learning about that, but I think it's needed to show more about it, because really to understand that this is a huge thing, and basically by the end of the decade the ALMA will be a new instrument, much more capable. And if you have questions, you should also ask your local ALMA node. Which brings me to 3 slides about the Czech node. So here on the map of Europe, Europe is special in the sense that, as I mentioned, there are 3 world regional centers, but the European one is actually a network of 7 nodes. You can see the location, and we have 1 node in the Czech Republic in the Astronomical Institute, and well, we are basically funded by the Ministry of Education as a research infrastructure, EU ARC-CZ, and we have people who are experts in solar observations and in galactic observations, and we have experience with other telescope as well, telescopes, millimeter or radio telescopes as well. You can see what are the main activities of the Czech node. So as I mentioned, the most important is user support, so it's on basically every level of using ALMA. When you need some help or assistance with the preparation of your observing project, or if you need help with preparation of phase 2 or with processing the data, etc. Also an important part is development of ALMA, and the Czech node is unique in the solar part. So the Czech node is the only node in the European network which has this expertise in solar observations in ALMA, with ALMA, and we even have this development programs I will show in the next slides. And we have access to HPC computer, so users can ask for access to that and use it for data processing and simulations, etc. So quickly through the solar part. So this is an important part, as I said, because no other European node has this expertise. So I think ALMA is the only ESO instrument which can do solar observations. You don't want to point any other ESO telescope to the sun, and as I mentioned, so from this reason all the European projects, accepted projects for observations of sun, goes through the Czech node, and the development studies, there was one in 2014 and 17 which basically helped to start observing the sun, and now currently we have a new one which led by Barta with the title towards high resolution solar ALMA images, and it basically is a study researching how to do it to be able to do solar observations with more extended configurations of ALMA. And finally, if I still have a little bit of time, this is what I am using ALMA for, and I think it's quite related to the topic of the conference. So this is about gas stripping or RAM pressure stripping of galaxies. So this is one of the most famous examples of RAM pressure stripped or jellyfish galaxies. This is a galaxy ESO 137001 in the southern sky Norma cluster. This is the HST image of the galaxy. You can see all these kind of tentacles or streams of young star formation extending to one side. You can also see the asymmetry of the dust distribution. And when you look at the system in other wavelengths, so this is an overlay of 3 of them. So probably the richest one is in green is H alpha, so ionized gas, warm ionized component in the tail. Then CO with ALMA actually observed in red. You can see there is plenty of cold gas through the tail, mostly compact regions of cold gas, but present to large distances, and this is just let's say a half of the tail of the known tail. And then in contours, if you can see it, there is X-ray. There is more. This is not the whole image of the galaxy. There is also H1, which is going to be published. There is also radio continuum tail, and this galaxy was observed also with James Webb Space Telescope. So you can see this is a mirror image of the inner part of that. So you can see all these filamentary structures. I think this part corresponds to that CO part here. What is RAM pressure stripping? Quickly, it's a general process in astrophysics. So you have an object which is moving at high speed through a medium. So in this case, we have a galaxy which is moving in a cluster filled with this intracluster medium at typically 1,000 kilometer speed or even higher in some cases, and this creates this dynamical pressure. If this dynamical pressure exceeds the gravitational restoring force, then the gas from the galaxies or even dust from the galaxies can be pushed or removed and form these tails of stuff. This obviously leads to quenching of star formation because you remove the star forming material, and then consequently this changes the type of the galaxies from blue actively forming stars to red and dead, and it depends on the environment. So in smaller clusters like Virgo, you can basically completely strip a dwarf galaxy with this process, strip of all its ISM, and partially spiral galaxies, and in larger clusters like Coma, you can even strip completely massive spirals. This is an old visualization. Basically, this is not really cold gas stripping or cool gas stripping, but this is a halo in a cosmological simulation, and you can see the infalling halos. But this gives you the idea about stripping and formation of this outflowing tails of material. And it's a multi-phase system. I'm talking about the gas which is stripped from the galaxies. So these are all the how to say in all these ranges, frequency ranges or wavelengths, the tails were observed and detected. So going from cold gas through atomic, warm ionized up to soft X-rays and hot ionized component. And there has been recently many new observations revealing the let's say, this complex and rich picture of gas stripping. And I thought I will bring this up because I think there is many similarities between the ram pressure stripping, gas stripping, and outflows or galactic outflows. So lately we know that cold gas or cool gas is important in outflows, in galactic outflows, and this is also true for the ram pressure stripping. And so both of these processes cause quenching of star formation and transformation to red types. Both of them strip or remove gas from the inner parts of galaxies to the surrounding environment. So both of them enrich the intergalactic or intracluster medium. The conditions of the events are quite similar. So the speeds of the outflowing gas is hundreds to thousands kilometers per second. They might be substantial, so a significant fraction of galaxy mass can be taken away by that. The stripped gas is a complex multi-phase environment, and the stripped gas or outflowing gas is mixing with the surrounding intragalactic or intracluster medium. The timescales, I think, are also quite similar. Probably they might be longer in the case of ram pressure stripping, but let's say 100 mega years, something like that. Both processes are more efficient in low mass galaxies. In both processes you can have reaccretion of material which was stripped or removed from the galaxy. It's probably more frequent in the case of galactic outflows, but this may happen also in the ram pressure stripping. You can have star formation in the outflowing gas outside of the galaxies, so the gas cools even though it's mixing with the hot surrounding gas. You can have seeds or parts of that gas which cools down and eventually may form stars. And there is even a connection to AGN in the case, or suggested connection to AGN in the case of ram pressure stripping. There are some observations or some studies suggesting that because of the basic compression or the effect of the ram pressure on the galaxies, you can cause inflowing motions of the gas into the central parts of the galaxies and maybe start AGN in those galaxies. So there are many similarities. So as I mentioned, molecular component in ram pressure stripped or jellyfish galaxies, this is relatively new thing, let's say 10 years ago. And it might be an important component. So this is again the galaxy from the first slide of this part, and this is the full extent of the tail. So this is over 60 kiloparsec, and there is still a cold molecular gas at 60 kiloparsec behind the disk of the galaxy, which is here. And so there are also many open questions which I think are quite similar to the questions about galactic outflows. And ALMA can give some responses to those questions. So we had this ALMA program, ALMA Jelly. We are working on that. Those are the questions, the main questions that we had, with which we planned the observations. And basically we had 28 galaxies observed, ram pressure stripped galaxies. And the main question is about the incidence of molecular gas in the tails and about its evolution, because we covered those galaxies based on H-alpha observations and on their morphology from presumably early stages of stripping to late stages of stripping. So you can see some examples here. This is optical view of the galaxy. This is how H-alpha looks like. This is focusing on the main parts of the galaxies. In some cases, the tails are longer, and this is correspondingly the CO. So you can see presumably early stage of stripping. There is some, you can see in H-alpha especially, this diffuse tail and asymmetries in the galaxy. You can see this also in CO. Then you can see some stripping, some tail already in development here, a longer tail in this case. Some very little leftover of H-alpha and CO in the disk and a tail, and then there is nothing in the galaxy, and you can have H-alpha or stripped H-alpha and CO in further in the tail. These are again a couple of examples of our observations. So I think we saw a couple of the galaxies in the previous slide. But again, you have a galaxy and you can have a quite long tail of CO emission. Here you see this was one of the galaxies of the previous slide, but there is stuff out here in quite large distances. This one is presumably very late stage of stripping, so the galaxy, the main galaxy is here. This is optical, this is H-alpha, and you see CO, you see these orange blobs, and in H-alpha these streams in the outer part of the tail, but there is nothing in the inner part. So this is presumably a late stage of the evolution, and still cold ISM or cold gas, which was stripped from the galaxy, survives in the tail. So I will stop my presentation with this slide, and I'm just saying or focusing here on the question about the origin of the molecular gas. I think it's common for the ram pressure and the galactic outflows, and I think in the ram pressure stripping, both scenarios, like a scenario of a direct stripping and formation in situ, or like through cooling of the stripped gas, may be true. And I think we need new data on cool gas stripping and cool gas outflows and new simulations. And obviously ALMA and next generation of ALMA and millimeter and radio interferometers are crucial for that. So I will stop here and thank you for your attention.
Thank you, Pavel. Questions?
Thank you. You managed to pack a vast amount of information in that presentation. It's fantastic to see ALMA getting a new lease on life. There's just going to be so much that it's going to be able to do in those new modes. So my question is actually about the science that you're doing with it. Mm-hmm. The gas stripping from the jellyfish galaxies is a fantastic place to explore star formation in a place which is quite different potentially to the conditions that it normally happens within galaxies. And obviously one of the themes of this meeting is about the stellar initial mass function, which we'll be hearing a lot more about in due course. Mm-hmm. Have you explored the rates of star formation or thought about ways of measuring the initial mass function in the stripped gas at all?
There are some studies about the star formation outside of galaxies, like for example in this galaxy, and there are, well, we are not the only group working on that. So there is also, I think I mentioned a couple of times in the slide, there is this Italian GASP collaboration. They have great results and a lot of observations as well. We, with the Jelly program, we should have more CO observations. So, but we are still working on that. But for this galaxy, I think it was published like the study of this blue star forming region in here. I think, yeah, you are right. This question, you have star formation in quite different environment because it's outside of galaxies. So some processes are missing, some other processes are present. I think we don't have a definitive answer on if it's different really. I think it might be because like looking here also you can like comparing CO, so cold molecular gas, and H-alpha warm ionized gas. You can, I think, have all different combinations as you can also have in the galaxies. So H-alpha with CO, no CO, etc. So maybe the process is similar, but well, we don't have a definitive answer to that yet. But this is one of the major and quite exciting questions. Maybe we need also better resolution to do this, but yeah.
Excellent. Thank you.
Thanks for the presentation. I have a question. What CO transitions are you using? Is there any difference, say, between going up to higher transitions, which maybe trace different shocks in gas?
Can you repeat the beginning of the question? Sorry.
What's transition for the CO are you using?
For
is there
CO.
Any, Is there any differences, say?
You mean for this? So the
jellyfish gas.
For the jellyfish,
Yeah,
basically the big observation. So this 28 galaxies. This is only CO221. So we had to decide about about the line. We thought CO221 would be the best one. ALMA is more efficient and at this frequency. So we only have CO221 in this study. So there are, I think, very few observations. We also have some old data which we haven't processed yet, trying to search for these higher density tracers like HCN, etc. I think there are some detections, but we have to work on that. But this would be connected to the previous question. I think in the densest clumps, I think it was for this galaxy. So we tried to cover some parts of that tail in this galaxy with also these higher density tracers and see, but we haven't processed that yet. But basically, I think what mostly exists is CO221. The gas collaboration, if I remember well, I think they have CO221 and CO10. There are some CO322, but mostly the low CO transitions.
Okay, thank you.
Hi, thanks for your talk. So I'm sorry if this is something I missed in the presentation, or if it's just a very naive question, but you've mentioned the similarities between outflows and ram pressure stripping. And so how do you disentangle the two? Because, I mean, on this image, I guess, fine, but some of the other ones that you showed, I wouldn't...
Right, so... I'm not I don't think that in our sample of 28 galaxies there is any, or maybe there was suspicion about one that it might be a combined effect of stripping and galactic outflow. So
so they're easily identifiable. It's not really
I
something...
would think so, yeah.
Okay.
I'm not an expert on galactic outflows, like how big or how extended they really might be. I know they might be on kiloparsec scales, but in our case, I'm not saying all our galaxies are 50 or 60 kiloparsec long. We have some which are shorter, but I think the overall morphology, it might be maybe a question for, like, for example, this one. I think this is quite strange because you have a galaxy and the tail, you can see H alpha is below CO. It's very, very long, but it's also very narrow collimated, so it's quite unusual for the ram pressure stripping. and most tails don't look like that. This might be a little bit similar, but not as extreme as that one. But yeah, I would think the morphology overall probably tells you, yeah, probably I don't know exactly.
Yeah, I would like to ask about, so are for these ram pressure stripped galaxies, probably there are some also AGN sources, or is there some kind of correlation, or at least weak correlation? Because I would expect that if there is like extra heating, so maybe this heated gas could be easier to strip in principle, right? So it's not so bound, at least naively, of course. So are there some studies on this aspect?
So I think this is accepted fact that the feedback should make it more easier to strip stuff because it's making it more diffuse or more disturbed. I'm not sure there is a study about an AGN really being observed at this, at RAM pressure stripped event. What I mentioned by my note at one of the slides was that the GASP collaboration, they claimed that there might be a connection between RAM pressure stripping and AGN, just simply from the fact that in their sample they saw jellyfish galaxy at the same time they were AGNs, or higher fraction of the galaxies were AGNs compared to a field sample. But
I think the maybe the most difficult question in this aspect is if this stripping somehow can trigger increased AGN activity, or vice versa, a chicken egg problem kind of, right? So that's but yeah, I think it can be interesting.
Yeah, but in clusters, I think RAM pressure stripping is it's easy to believe it exists, and the pressures are so strong that it clearly will strip the galaxy or the ISM at least to some radii. So you, in principle, you don't need an AGN to make the stripping active or efficient. So maybe the question vice versa is maybe more interesting.
Hi. Since you have like H alpha, I know you need another mission line, but have people been able to estimate the metallicity of like the tail?
I think there are some works, and I probably need to study it more, but I remember basically there was no surprise really, because you are stripping the gas from the galaxy, so at least some early measurements showed that there was an increased metallicity also in the stripped gas. Maybe there is more works now, but I don't know about
Sure,
it.
thank you.
Hi, thank you for your talk. I was very interested in the similarities between outflows and RAM pressure stripping that you showed, and you mentioned especially the molecular gas and how it's crucial. Out of your 28 galaxies, I believe, in how many do you see molecular gas? Like, do you detect molecular gas, and do you see like trends or relations between how much molecular gas there is in some galaxy properties at all, or not?
So we are still working on that. This is one of the questions, but so we don't have 100% success in detecting molecular gas, but then you can also differentiate between whether we detect the main galaxy and a tail. So I forgot the numbers, but I think we have like 4 galaxies with non-detections.
Okay.
And the numbers for galaxies and tails is different, but yeah. But in some cases it is quite compared to the galaxy, this ESO 137, where you see very rich, there are hundreds probably clouds throughout the tail. We might have a tail which has just one strong clump somewhere like 30 kiloparsec away from the galaxy, but this seems to be real because the spectrum is really nice. So yeah,
okay.
So it's a huge variety. Yeah.
Thank you.
Okay, I know that there are more questions.